Hello, yeah, pushing on with the 2021 PAT, we're up to question 17. In Einstein's theory of gravity, light passing a star of mass m at distance r from the centre of the star is bent by angle theta, measured in radians as shown in the diagram. Assume that theta depends on all of, well, we got this relationship here, they're just saying things. Lambda is an undetermined dimensionless constant. Okay, so, we're doing dimensional analysis in order to get this. So they're all going to have to add up to zero because we're just measuring something here in radians. So we need we need to know units of g. So g, well, if we were going to go off of our Newton's law of gravitation, then that's going to be fr squared over m times m. So in terms of units, we've got newtons meters squared over kilograms squared, because newtons are kilograms meter per second squared. So we've ended up with meters cubed, seconds to minus 2, kilograms minus 1. So that gives us, that's the g bit. Then we've got kilograms to the alpha, meters to the beta, and meters per second to the gamma. So all these have to add up to 0. Well, kilograms, so we've got alpha is 1 because we've got minus 1 plus alpha is 0. Then for meters, we're going to have 3 plus beta plus gamma is equal to 0. And then for seconds, we've got minus 2 plus gamma. No, minus 2 minus gamma, sorry, is equal to 0. So gamma is minus 2. And that means that beta is minus 1. So that's good. Don't mind a bit of dimensional analysis. Right, so that was 1 minus 1 minus 2. So let's write that down here just so I can see what's going on. Then we've got in SI units, that's G. Okay, neglecting any spatial extent of the star, taking lambda is 1 and that being the mass. Determine R such that light is bent so much it falls directly into the star. So if it's falling directly into the star, then we've got theta is pi by 2. So we just have to plug it all in then, don't we? So we're going to have pi divided by 2 is equal to, well, lambda they've given us as being 1. G is 6.67 times 10 to the minus 11. Mass is just straight mass because alpha is 1. So multiply by 2 times 10 to the 30. Then we've got to divide by R. Divide by R. And divide by c squared, multiplied by 9 times 10 to the 16. So rearranging all of this, we'll have, that's going to be equal to, well, we'll put the r up there and put the, multiply this by 2 and put a pi on the bottom. That's going to give us what r is. Just getting rid of that, which means what we got for tens, we got a minus 27 and a 30. So we've got 10 to the 3. Then we've got, what have we got? We've got a 2 times 2 times 2 times 6.67 divided by 9 pi. So we just have to type all that in and get what we get, which comes out as, that was R is equal to 944 meters, so 940 meters to two significant figures. It's just plugging in numbers, really, isn't it? So that was a pretty straightforward question. Got us going after the hideousness of question 16. Right, this looks like the geometry question. So we've got to find the area of the dark regions in terms of, right, so at least it's a simple idea. So we need to do the big circle minus 2 medium circles minus 2 little circles. This is what we're trying to do. We know the big circle is pi r squared. We know that the little or the medium circles are going to be a quarter of pi r squared. So we're doubling that. So we're taking off half of pi r squared. And then we've got 2 of these little ones. So let's call these radius r then, little r. And we can say we've got 2 pi little r squared. we have to take off. Right, so how are we going to get this little r in terms of big R? Right, well, we're going to have to draw on what we can do with this. So put all the centers on, and then we'll see what we end up with once we draw on all of the touch points. So we're going to have the lines that connect up all of the centers, and we're going to have the lines that go out to the outside. So we're going to have to work with those. And we're going to, right, so it's pointing us towards triangles in the middle. Let's draw out that. So we've got right angle triangles. So they're all the same right angle triangle. So it doesn't matter which one we pick. So if we have this, so I'm just looking at this one here, this triangle. So we've got the right angle in the middle. This is r over 2. What we got going, the hypotenuse is going to be r over 2 plus little r. And the vertical side is going to be big R minus little r. So we can Pythagoras all of this. So we can say that r squared over 4 plus r squared plus little r times r. You know, we have to do this on multiple lines because I don't really have enough space here. Is going to be r squared over 4 plus r squared plus little r squared minus 2rr. Right, so we got that cancels with that, that cancels with that. This is all good, isn't it? We can get rid of a whole load of r's, but first of all, let's do 3 big R little r is equal to r squared. Get rid of a couple of r's, so 3r is equal to r. So we just need to shove that in here. So we've now got pi r squared over 2, dealing with the first two terms, minus 2 pi times little r squared. So that's r squared over 9. So that is pi r squared a half minus 2/9. So that is 9 over 18 minus 4 over 18 is 5 over 18. 5 pi r squared over 18. Well, that was pretty straightforward geometry question for 5 marks. What we got now? Where are we? Question 19. Sand is poured at a constant rate onto a flat horizontal surface. It forms a pile in the shape of a cone with a constant slope. Right, so we're getting this sort of thing going on where we've got this constant angle there. If r is the radius of the base of the cone, find out r varies with t given that r0 is 0. Right, so that's our r. Right, we've got then the, right, so we're saying, what were we saying? It's a pouring on a constant rate. So dv dt is going to be a constant. So let's call that, I don't know, a. So that's our dv dt. What am I doing now? We've got that, well, let's have something about the volume. The volume is going to be a third of pi r squared h. I don't know if we're going to need that, but let's just write all these things down. And we've got this, let's say about the slope. It's a shape of a cone with a constant slope. So if that is theta, and we've got h, at the moment I'm sort of just writing things down because I don't know what I'm going to be doing yet. So h is r tan alpha, isn't it? Yes, so r tan alpha, theta. R tan theta is h. So we've got all of those things. Right, so what have we got with, so, well, v is a times t. We can get that off of there. So what else have we got? Because we're starting with a 0 volume at time is 0 because r is 0 at time is 0. So we don't have to worry about adding a constant onto here on this integral. So what have we got? Well, we can now put that in there, can't we? And we can say that a times t is equal to 1/3 pi r cubed tan theta. Right, what are we trying to work out? We're trying to work out r as a function of time. Right, well, we're there then, aren't we? So we've got r is going to be 3at over, let's scroll down a little bit, 3at over pi tan theta. And we've got what, cube root of that. That's r as a function of time, right? If it takes a time t1 for r to reach r1, how long does it take for the radius to reach 2r1? Right, so let's read that again. T1 to get to R1. And then if it's going to double the radius, yeah, we're doubling the radius. So if we're doubling the radius, then we are, well, we've got a connection here between, where's the cube? We're cubing it to get to time. You cube the radius to get to the time. The radius has doubled, then we must have 8 times the amount of time, because we've got time is proportional to r cubed. I mean, that's what we wrote out here, and essentially here. So yeah, we've got that. So radius, that means, so yeah, time must go up by 8. So we've got 8t1 is what we need. Oh, okay, that was fine. There's that sort of stabbing around at the start for part A, but it quickly became apparent what to do, but it wasn't immediately obvious. Sometimes you get this with questions. I think I've say this quite a lot of videos, that don't necessarily know where you're going at the beginning. You just sort of do stuff and see what happens. Right, expand that where c is a positive integer as a polynomial in x up to and including terms involving x squared. Right, so we need to get this a outside. So we're going to a plus bx, so you want a 1 there, is what we want to do. So that's going to be a to the c, 1 plus b over ax to the power of c, which is a to the power of c times 1 plus, well, bc over a times x, plus 1 of c minus 1. Then we're going to have, well, you have to put that over 2, and then we'll have b squared over a squared times x squared. That was as far as I wanted, wasn't it? Yeah. Plus bits. So we've got that. All right, so we've done that. If the coefficient of the x is 0 term is equal to 1 over 16, so we're saying a to the power of c is 1 over 16. B is a quarter. Okay, let's just add that to the list. And then the coefficient of the x squared term is 3 over 32. So the x squared term is a to the power c multiplied by c minus 1, b squared over 2a squared. That is 3 over 32. We have to work out what a and c are. Right, okay. So what can we say about... All right, so c is a positive integer. So a is going to have to be either a half or a quarter, isn't it, in order to get it to 1 over 16. So what would that make for any of these? If we add that, then c would be, that would be 4, or c would be 2. They're our only options, so I reckon we just stick these things in and see what happens. So let's start with the first pair then. So a is a half and c is 4. Oh, well, we know a to the power c is 1 over 16 anyway. So we've got 1 over 16 multiplied by, so that would be 4 times 3, so by 12, multiplied by b squared, so that's 1 over 16, divided by a 2, and then divided by a squared, which would be like multiplying by 4. So what does that come out as? We're going to have 24. Actually, I want to, yeah, let's do some more cancelling first. So let's put this over 8, which means we're going to have 3 over 2, which is 3 over 32. So yes, that one works. So I can only assume, or so I'll tick that one, it's that one, that column rather than row. So a is equal to a half and c is equal to 4. Yeah, I'm not too sure I would have solved that otherwise, having that power, but there's only 2 values a can take. So yeah, that certainly helps matters. All right, so that's question 21 done. Where are we now? All right, question, oh no, it was question 20. We're on to question 21. A pinhole camera consists of a box with small aperture, diameter x. A point light source P is at distance u. Yeah, this is all we've got on the picture. Projects an image on the screen, distance d. Yep, so it's just describing the picture. Wonderful. If diffraction is ignored, what is the diameter S1 of the spot projected on the screen? Okie dokie. So if we've got no diffraction, we're just going to have straight rays, straight lines for our path for the light. So it's going to go from P, it's going to clip either edge of the aperture and then create a spot on the screen. So just blowing that up somewhat so we can actually see what's going on. This is, what did I say? S, right, so this is our S1. This here at X is the aperture. This is, that's U, and then that is U plus D. So we've got similar triangles going on. So we've got the X over U is S1 over U plus D. So S1 is going to be X U plus D over U. Right, so nice starter. If D is much bigger than X, diffraction of light of wavelength lambda by the aperture produces a distribution of intensity. Right, so now we're putting the diffraction in. It varies with angle theta, measured in radians from the z-axis. Right, marked on, all right, so off of this line. Right, okay, right. So they're saying this is a new point source, which is why they put that in. So we've got a new triangle going on, starting at the aperture. Wonderful. So we're probably going to be doing the same thing. And they've given us the angle. Right, so on here, they've given us the angle, which is that. So what are they actually asking? What is the approximate diameter S2 of the central peak of the diffraction pattern projected on the screen? So this is our new spot. So rather than having S1, we're now saying, so S1 was just going straight lines from P. This is now saying, well, say we've gone to X and then we've diffracted out. This is now, right, let's draw this a bit neater. So that's now S2. This is D. This is, what did they say it was? Lambda over X, but 2 lots of lambda over X. So we can do the same. Are we doing similar triangles again? No, we're not doing similar triangles again because we don't have anything in the height. So it's going to have to be trig, isn't it? Because we've got an opposite and an adjacent. So we're going to have tan of the angle multiplied by the adjacent. Yeah, so it's going to be S2 over 2 because we just got half of the angle. We want to make it right angle, don't we? We want to split it down the middle. It's going to be D tan lambda over X. So, oh, well, we just multiply through by 2 and that gives us what S2 is. Okay, now cooking on gas here. Now we've got, assume that the effects of A and B can be combined to give S3. Find the pinhole size that produces the sharpest image. Okie dokie. Right, so we need sharpest image means smallest then. So we need smallest S3. And we've got the S3 squared is equal to S1 squared. What was S1 squared? S1 was X U plus D over U. So X squared over U squared times U plus D squared. And S2 was 2D tan lambda over X. So 4D squared tan squared lambda over X. So yeah, we're going to have to differentiate this, aren't we, to minimize it if we're going to get our optimum image. Don't like the look of having that tan there. So, but I haven't told us pinhole size that produces sharpest image. But I mean, this is light that's going through, so lambda's very small. I mean, you can't, how big a hole do you make with a pin? Can we assume, I don't know where else to go rather than saying that lambda's a lot less than X and then doing a small angle on tan, and then it gets rid of tan in our differentiation. I mean, if it's light, I mean, we're talking about, 500 nanometers or something. So, I mean, that's tiny. So pins, but I don't know how big pinholes are. But if we don't do that, okay, we can differentiate it, but I don't fancy our chances of then solving it at the other end to say what x is going to be. So, right, let's assume this and then see what we end up getting and see if it gives us something which appears to be a lot bigger than the wavelengths of light. Let's see what happens. So if we go with that, we can say that tan lambda over x is equal to lambda over x. That's what we're going to have on all of this. So that means we're going to get x squared over u squared, u plus d squared plus 4d squared lambda squared over x squared. So let's differentiate all of this. So we'll have 2 lots of ds3 by dx is going to be equal to, well, 2x over u squared, u plus d squared. That will become minus 8 d squared lambda squared over x cubed. So we want this to be equal to 0. Let's get rid of these things. Get rid of those 2's. So just imagining that being an equal sign in the middle, in order to save me a bit of space, we're going to have x to the power of 4 is going to be 4u squared d squared lambda squared over u plus d squared. So we can double square root that and get that x is the square root of 2u d lambda over u plus d. Right, is that going to fit with our, approximation here? So, I mean, we're square rooting something anyway, that's something that's really small. So, I mean, even with u and d, okay, u times d is bigger than u plus d. Well, I suppose it depends on what they are. But still, you've got something small, but we're doing a square root here on the lambda. So that's going to be okay then, because it's going to take orders of magnitude off of that in the negative sense. So x is going to be a lot bigger than lambda. So I think we're okay with that. I think that's, yeah. Otherwise, we'll end up in a right mess. Can you imagine if we were differentiating this here? And then getting all of those, it's all like sec stuff and things like that, isn't it? For when you're differentiating tan, because you get a sine squared plus cos squared over a cos squared. So it all ends up being sec, and then you've got to square it. So, yeah, I think that'll have to do. It's quite a tough question, that one. The last part, certainly. So I'm going to leave that there because I think we got like 2, 3, 4 questions left, so I'll stick those in the last video. That'll do for this one. Not a bad bunch, but yeah, mixed bag. Some bits were quite easy, some bits less so.